Okay, let's start again. Just before I move on to the next condition, I just noticed a small typo here. The electrons are moving in this direction. The current is in that direction. Okay, so this current is pointing in this direction. It's just because these are electrons going in this way. Okay, so let us consider now the situation where the B junction is still forward biased, but now also the BC junction is forward biased. So this means that VBE is positive, so that the BE junction is forward biased, but also VBC is positive, so that the BC junction is also forward biased. This means VCB smaller than 0. And so using the same approach we did previously, I'm trying to transform this in something that has the emitter inside. So we use the same technique. VCE can be written as VCB plus VBE. And because this is negative, this means that VCE must be actually smaller than VB. So VB is still positive, remember? So in the end, effectively, what I'm saying is that we are in this situation. That VCE is in between 0 and VB is VB on, remember, that we said previously, or say 0.7 volts. So the situation we are describing really on this diagram, if you like, is when VCE is really approaching the 0 that is here. So it is actually, now you may realize what I'm talking about is this region here that I've already drawn. The situation when VCE is actually quite small in between 0 and VB. So on the diagram, where does it sit? What is happening on the diagram? So VB is this value here. So really, I need to bring the Fermi level of the collector in between the black dashed line and the red. That would represent what I'm trying to describe. So we've said, effectively what we've said up until now is that if I move this up to effectively this red line, we are still having a very large current flowing through. This point here, the knee, let's say, of this behavior that I've anticipated, happens when VCE is equal to VB. That is VBC effectively 0. You see, when VCE is equal to VB means VCB or VBC is 0. So from that point on, what is, if I was to draw, don't want to make a mess of the diagram, I will do it in blue. So let me draw a situation where the Fermi level is slightly below, in between the black and the red. And so this is an N-type, so I should draw it like that, something like that. So you can probably appreciate that the more I move this up until really it reaches the black line, so the Fermi level here represented by this line, as soon as this effectively reaches the black dashed line, what will happen is that I am effectively moving along this line. So as I move upward here, the current will start dropping. It's not difficult to understand based on the fact that we said this huge current IC that we see is because there is this energy drop on the collector side. What we are describing in this region of the plot is that the collector energy diagram is moving effectively and coming, if you like, aligned to the base, the conduction band and the valence band roughly. And so this effectively has the meaning of no more energy drop. That was the reason in the beginning of this large current. So that's why here the current drops like that. As VC moves from this value here that corresponds to, remember, VC at this point, where is the knee, VC is equal to, what did I say, VB. So between these two, the VB and 0, the current will drop dramatically now. Okay. What we have described is the saturation regime, what we call saturation. So the transistor cannot do anymore the nice things we've seen in the active mode. That's what basically is the saturation mode. This means in the saturation mode, this doesn't hold anymore. The IC that you will get will be smaller than the expected one. So this is saturation. Let me remove some things, otherwise we may get confused. I'll remove these things here. Okay, so we've done active mode and saturation. Let us have a look at the cutoff mode. So now we are considering the case where we have the BE junction is in reverse mode, and the BC junction is also in reverse mode. This is called cutoff. You can see all the junctions are reversed. So really there is no current going anywhere. That's the point. So I'll write the conditions here. So the B junction reversed means VBE smaller or equal than 0. We will see that for us is equal to 0, what it means. VB equal to VBE. And the other one, that the BC junction is reverse biased, means also VBC smaller or equal than 0. Again, we do the same story. We try to transform this one into something related to the emitter. So remember, this means VCB bigger or equal than 0. And so VCE, which was VCB plus VBE. Now, we said, for us, VBE, we never consider VBE negative. Maybe equal 0, yes, when we switch off effectively, there is no current through the BE junction. So really this for us means roughly 0. VCB, well, VCB is positive. And so VCE means must be positive. So really the cutoff mode means VBE reverse biased, 0 for us, and VCE positive. So So really, going back to this diagram, let me clean up the diagram as well. So this situation, VBE, let's say 0, and VCE positive, could be represented here simply by the fact that I'm moving this up so that the Fermi level now aligns with the dotted dashed line. We've briefly considered this before when we were qualitatively trying to understand the property as a valve, if you like, of the BJT, as a switch. Obviously, what we understand is that if I turn off, if you like, the BE junction, the transistor will not work anymore, will give zero current, obviously. The only current that may pass through is the reverse current, the one that we indicated previously, we indicated as IC0. That's the only current that may pass through the transistor. It's a very small current due to the reverse bias condition. So on this diagram, the only thing I need to change is really to shift upward these things so that the Fermi level is here, and so things will look something like that. But in this situation, this B junction is off effectively. There is zero bias across, and so there is nothing coming on the other side as well. Whatever you do here, you won't get anything, because these carriers can't go over the barrier, because this junction is off. So what do I do here now to represent that? Well, there is no current. The only current is IC0. So really there is a very small current here, something like that. So while all this region represents the saturation, all this region down here is not permitted to the device, and the only thing you can get is whatever VCE you use, you will get a current that is effectively IC0, this reverse current of the junction. Very small. So to qualitatively represent what we said, since we are talking about moving this up and down, so we can now realize that the complete view of the characteristics of the transistor on this IC VCE plot is represented by a number of these curves, sorry, something like this. Where IB here increases like that. So each curve is related to a value of IB, and IB, when IB grows, also the corresponding IC grows. Based on what we said, if I fix VCE to a fixed value, by changing IB, I move along this line. So I can go from active, the active region, if IB is big, and VBE is VBE on effectively, the B junction is forward biased, to down here, eventually, when the VBE is 0, and the B junction becomes not anymore forward biased, and so we go into the cutoff regime, where the transistor doesn't pass any current anymore. Okay, so that's a nice way to make a switch, by just operating on the base, either IB, there is IB, there isn't IB. I can pass IC, a large IC, or nothing. Okay, the final mode is more just to complete things rather than the real use of it, because it's just the mirror of the active mode. So the last mode is the inverted mode, which is the B junction is reversed biased, and the BC junction is actually forward biased. You can see that it's the mirror of this. And this is called inverted. And what we are doing is we are swapping the role of the B junction and the BC junction. So now is the BC junction that is forward biased, and this is reverse biased. And the effect that this will have is that simply all the currents and all the voltages we just gone through have to be changed in sign, because now are these electrons that will flow in the. So you can actually go and have a look at the active part that we analyzed and swap the names of C and D, and everything holds true. Okay, so I'm not going to go into the details here. It's as simple as that, really. Is exactly the mirror of the active situation. And so concluding, you will have it anyway on my notes. So to conclude, the final characteristics are, okay, so the final characteristics, I'll leave that. I can remove this. So what we've seen, and we can do it here on a nice plot, just to VBC. So we have VB and BC. That's what we've been discussing about, to understand whether B is forward or reverse biased and BC is forward or reverse biased. Basically, we've been talking about VB and VBC. And so on this plane, saturation is here, active mode is here, inverted mode is here, and the cutoff mode is here. And just to, we've seen the characteristic IC VCE on the screen, which I will show you now from a real transistor. But there is also another characteristic that, which is this one here. So we've discussed the output, if you like, characteristic, the IC, which is the current in output coming out, the large current, versus VCE, and the parameter there was IB. So this is called the output characteristic of the transistor. But the other thing we didn't discuss, because we had it in our mind, is also how that relates to the input characteristic, which is, in this case, was the base. We've been saying that what is controlling the resistor is IB and VB and so on. So here is the plot of VB, this is VB, versus current. This is the plot for IB, and this is the plot correspondingly for IC. So from this graph, we can realize how when VB is turning on, if you like, the PN junction BE around 0.6, between 0.4, 0.8 now here, you see that IB and IC are perfectly proportional, parallel to each other, and the proportionality factor is this beta that we discussed previously, which depends on the transistor, around 100, we said. So it is in this region that the transistor is active. Okay, if we come down here, we are switching off. VB becomes too small, so the B junction becomes effectively reverse biased or not conducting anymore anyway, and so the transistor also switches off. When there is too much current, IB is very large, which means effectively that VCE is actually dropping. Now, it's not easy to see here, but that's what in turns means. You see that the transistor cannot provide anymore the corresponding IC that would be required, and so it saturates. That's the saturation. That's not the best way to see that, probably, but everything is also on this graph. That's what I want to say. This is the one that we were watching previously. So IC versus VCE, and you see the saturation regime, the cutoff regime, and you can see that each curve corresponds to a specific value of IB. There is one interesting feature here, which I only briefly mentioned previously, which is about how flat these curves are. As you can see, these are not really flat completely, but have a slope. And actually, that's a nice feature of the common emitter configuration, is that if you prolong these lines backward, they meet in one point. That is called, as you can see here, is indicated down here. There is a break on the plot here, and very, very negative. There is this voltage VA. VA is called the early voltage, VA, and this depends, it's a very rough approximation, is minus E NB. This is the density of the dopants in the base, the width of the base squared over the dielectric constant of a semiconductor. So what we are saying is that in this region there is a slope, which we could indicate as DIC over dVCE. So this is VCE IC. And what we've realized from this image I've put there is that this slope will meet somewhere here, VA. All of them, all the possible characteristics meet there. So the slope really is proportional to 1 over VA, isn't it? The farther VA it is, the flatter this becomes. So this is a kind of an interesting realization. If I need this to be flat as I want, I need to play with VA. So dope, increase the doping, or increase the width of the base, and so on and so forth. Okay. Okay, so this is a qualitative analysis of the BJT transistor seen from using the common emitter configuration. That is the one that we will be using a lot. And so now I wanted to, based on the beautiful things we've learned, do some practical applications of this transistor, because in the end we need to put the transistor in a circuit to, in the future, next week, use it for an amplifier. So let me remove all this stuff. . Okay, so let's summarize all the beautiful things we've said So the first thing from Kirchhoff current law, we had this relation between the different currents of the BJT. We also said that when VBE is roughly 0, whatever happens to VCE, we are in cutoff, which means IC is roughly 0. And then when VBE instead is roughly VBE on, which could be 0.7 volts. We will often use 0.7 just because it's quite common. But remember always that in the end, you need to use what the transistor from the data sheet. You need to take this number from the data sheet of the transistor. So we have active mode if VCE is bigger than VBE. And in this case, IC is beta IB, and IC is also alpha I, where alpha was beta over beta P plus 1, and also maybe I will add I beta plus 1 IB. While this could also lead to saturation if VCE is smaller than VB. Okay, so what I wanted to do now at this point is to analyze some common emitter configurations with increasing complexity. Increasing complexity, you will see means adding always a resistor effectively, so not so complex in the end. With the final target is to try to analyze the circuit so that I can define the quiescent point, so the operating point of the device on that output characteristic we've seen previously. And we will also try to discuss each circuit in terms of stability. The stability comes into play because of these designs we will see, because the important parameters we've just learned about, beta, VB on, these all depend from temperature, for example. Depend obviously from the transistor. They vary from transistor and transistor of the same model. So there is a question there. What happens when I make a design and in my mind, it's according to the data sheet, I'm fine, but these numbers may vary from transistor to transistor. What will you do? What happens if the temperature changes? So we need to consider the stability of the design as well. How well, in the end, the circuit we will build will actually operate at that specific IC and that specific VCE that we were planning to. So the first one is the simplest, and this we will call it common emitter 1 fixed bias. So this circuit is extremely simple. We have now I'm overdoing it in the sense that I'm drawing all the power supplies, but in the end we will remove them. So this is RB, this is RC. So this is my transistor, B the base, the collector and the emitter. And this is VCC, and this is V in. This is what we called IB, and this is what we called IC. So what equations do I write for this circuit in order to be able at a certain point to define the, the quiescent point of the circuit, where it will end up operating at. So first of all, remember that from what we said, the transistor will be active if VB is around VB on. So VBE must be roughly VB on, and VCE must be bigger than VB. So under these circumstances, the transistor will be active, and so we can apply these formulas to do the analysis. So under this assumption that I'm in this condition, that the transistor is active, I could write first Kirchhoff voltage law related to the input mesh. As you can see here, the input mesh is actually represented by this part of the circuit. We know that VBE is VB on, so I could write V in equal RBIB plus VBE on that's it. So the first KVL is related to this mesh. The other equation I need to remember is that IC is beta IB. So you can see that this equation, say that I know V in, say that I know VB on from the transistor, for example, I know RB, or I know IB, I could define IB from here. Depends what I know. If I knew RB, I could define IB from here. If I knew IB, from this equation I could define IC. And then I have another Kirchhoff voltage law that relates now to this mesh, the output side, let's say, which where I could write VCC equal to RCIC plus VC. And this will define, if I know IC and I know RC and everything else, this defines VC. I'm doing this in an arbitrary way, if you like, but just to show you that these equations define, in one way or another, in this case, these two, define the quiescent point, that is VCE, IC. So it's a specific point on the IC-VCE characteristic of the transistor. Actually, if you look at this equation, this should remind us something. We have given a name to equations like this when we deal with a component that is nonlinear. How did we call equations like this? Where there is an important parameter, for example, IC, that relates to the output characteristic, and there is another parameter that is the independent variable of that important characteristic. We've called this equation the load line, or maybe what I will write now from here by explicitly writing the dependent variable that on the output characteristic is IC in terms of the independent one that is VC. So you need to invert this relation and write IC equal VCC over RC minus VC1 over RC VC. So you see, this is what we used to call, we've seen it with the diodes, with the PN junction, this is the load line. So one more thing I could do at this point, just to continue the approach, let's say, is to draw here, to draw the characteristics we had drawn previously. So this is IC, VC. So the load line says this is the intercept, VCC over RC will be a point up here. And you remember what we used to do with the load line is, it will be difficult to draw a line with a slope minus 1 over RC, if we knew RC. The best thing to do is to say, what is the VCE required so that I is 0? VCE must be equal to VCC. And so I pick here where is VCC, and now I need only to draw a line. This is the load line. So in the end, this circuit will settle based on the values of RC, RB, VE, and VCC, and so on a specific pair, VC and IC. But that pair, remember, has to stay on the load line. So this means that this could be the possible Q points. Q always stay on the load line. The specific Q in the end depends on the specifics of the circuit, so the value of RC, RB, and so on and so forth. And so, for example, in the end, let's say this could be the Q, and so this is in the end VCE, and this is in the end IC. But I think this fact that Q could move along this line is particularly interesting also from the application point of view, because if you remember, down here is the cutoff regime where the transistor goes off. Let me draw here this line. This is the saturation part. So really you can see that I can drive through the load line. I could bring, depending on the specifics, of the circuit, the values of the components, I could bring the transistor from cutoff, off, active, saturation. So I can explore effectively all the important mode of operation simply by changing RB, RC, or VIN, or VCC. These are the things I can play with. Note, and this is quite interesting, in general, you see this is on this diagram drawn, it seems that this is IC sat. The maximum current that the transistor will ever be able to deliver when it's saturating. You can see here that this value is very close to C over RC. So really, in our mind, when we think, to the saturation regime, let's think in terms of load line, and you could, in very good approximation, you can actually say that IC sat is VCC over, in this case, RC. Whatever is the output circuit, remember that this term comes from analyzing the output mesh. So in this case, in good approximation, IC sat is that. The reason is, you can pick up the data sheet of any BJT, you will see that really here I've over-exaggerated this part, the saturation part. If you call this as VCE saturation, you will see that this VCE saturation is roughly of the order of 1 volt, 0.5, 1.5, it's around this value, around 1 volt. Oh, the way we move Q along this line, based on, you see, what we are doing here is IB grows in this direction, and correspondingly you are on another curve. So to move from here to here, it means I'm increasing IB. So I'm doing something on the input circuit, either changing RB or V. From this brief exploration of this very simple circuit, we also realized, we said it, but I didn't probably kept on stressing it. So we can explore all three modes here: cutoff, active, saturation. So if I want my transistor to stay in the active regime, when we will do the amplifiers, that's where you want to be. A very good choice is to stay, design the transistor in such a way that Q is as far as we can from cutoff and saturation. Where would you put Q? Exactly in the middle of that region. So if I know that the saturation is, most here is 1 volt, VCC is, let's say, 10 volts, is big. A very good choice, always, generally, from the design point of view, is to choose VC to be, I need to stress this, unless has been defined in another way. Is there another condition that imposes you to define VC differently? But if it's not defined, it's a very good choice to impose VCE equal to half of VCC, so that you are effectively in the middle of this plot. This means that Q will end up being far from the saturation and also far from the cutoff. Because remember, Q has to move along here. So if I be okay, before I have an example. I was planning to do it here, but I understand there is no time for that. So I will leave these things for later, and I will have to put them in the post-lecture video. So I have a practical example of design using this circuit, design a transistor in order to. Now let me just finish on this. Let me touch the point of stability now. So what we see now on this circuit is that to be able to solve this in this configuration, I need to know beta precisely, because I define IC and IB are defined through beta. I need to know beta very well. And also I need to know VB on. So let's say that I've done the analysis of the circuit. I have an example, as I said, practically when we do the calculation, and I will put it later on the post-lecture video. Actually, I have a lot of examples with the practical calculation because I wanted to do also other configurations, but all will go on the post-lecture video now. It's a lot of it's practical calculations, so there is very little. We've done the concepts. It's more about now putting everything into action. So you need to know very well beta and VB on, and these two parameters in this specific configuration are crucial in defining IC and VC. This means that this design suffers enormously from any variation that beta goes through or VBE goes through. So if, for example, beta, you thought it was 100, but is 120, IC will change by 20%. So you won't be here. You will be you need to move 20% along the load line. You will move here. What is happening? Where I'm moving, toward what? And that's not good if I wanted to do with this an amplifier. Same with VB on. So this is very easy. It's a nice circuit, easy and simple for fast applications. But remember, this is very prone to the risk of, what will be happening in reality may be very well different from what you thought of by design, okay? Because it has this intrinsic dependence from beta and VB on. Okay, I will leave all the nice applications for later. And just to conclude, because we don't have much time, to conclude, yeah. Okay, I can do this. What I'm going to mention now, still on this, is a nice application, still related on this type of configuration, but that instead of thinking of using the device in the active mode, uses it as a switch. So imagine to make a small change here in this circuit, and do this. So you have now a switch. Say you've defined the circuit to operate when we were using Vin. The circuit is in this point. But you have also a switch now. So when the switch is in B, this is Q of B, when the switch is in position B. If I now put the switch in position A, what will happen to the output, to current in output? So with Vin, we follow this analysis, and we know that the quiescent point is here, in the active regime. We'll go here. Yes, we'll go in cutoff. Because basically I'm saying on the base mesh, there is no voltage anymore. So there is nothing that is putting in forward bias the B junction. So we are in the situation that we call the cutoff. On the collector, there is voltage. If you go back now, unfortunately it's not here, but that's what defines cutoff. But we don't need to go there. We can look what's happening here. So if there is no power supply on this side, so this is now here, IB 0. So IB 0 on this diagram is represented by the IC equal IC0 curve. But remember, we are moving along the load line. So this means I'm going here. So that switch will let me move my circuit from this point to this point. As you move the switch, this does that, the system. So you will have no current, either no current through here, or a lot of current. The whole point of using the BJT is that IB is much smaller than IC, okay? So you are using low power to power something where there is a lot of power involved. That's the whole point. IC is roughly hundreds of times bigger than IB. Okay? So I need to stop here. Is there any question on this? This is quite important. There is an application that we will do later on. But is this okay? So with the switch, you can. This switch can be a switch that you flick, or could be even something else. Could be Arduino. Could be Arduino, that you tell Arduino go high or go low. High is 5 volts, low is 0 volts. So this thing could be many things. But with something, the idea is using very low power here, you are piloting something that could involve a lot of power. Actually, we could make it even more fun if you wanted, then use this to pilot something else that is even more powerful. So you could add another stage. I will show you an application using a relay. A relay, you maybe know what it is. A relay, it's an electromagnetic switch, let's say, operated by electricity. It's a switch operated by electricity. So you could put here the relay. So you could use low power to operate something that requires medium power, to operate something that requires a huge power, like a motor. You put the relay here, where RC is. Okay, I have an. I think at the end of on the 10th lecture, I will put this application with relay, which is kind of interesting. Okay, those of you that are interested, I'm going to lecture theater C regarding the feedback that I wanted to, discuss. How, if there is anything to improve now, based on the survey, you remember. So those of you that are interested, I will go to RBB LTC, which is free, so 2 floors above. And otherwise, I'll see you next Tuesday.